I'm going to introduce our third speaker, is Camille Maumet. She's a research scientist in neuroinformatics in the MPen team in Ingria of the University of Rennes in Iriza in France. She studies neuroimaging reproducibility. Current research, she is focusing on the variability of analytical pipelines and its impact on our ability to reuse and use brain imaging datasets, which is obviously quite topical. Camille is also an open science advocate and participates actively in national and international communities, including BIDS, keep the team going, my friend, BrainHack, and the French Committee for Open Science. And Camille, I'm going to hand it over to you, my friend. Go ahead, share your gig.
Thank you very much. So I'm going to first try and share my slides. Let's see how this goes. And then, okay, can you see my slides okay? Yeah, and is it moving to the next one? Great, thank you so much.
It absolutely is.
So hi everyone, I'm quite excited to be here, even if it's early in the morning. I really like that I get the chance to be on a time zone that I'm not usually in. So here we're going to move back a little bit from Neurodesk, and I think it's a nice transition going from Neurodesk to this talk. And we are going to ask ourselves, how can we increase computational reproducibility? And I'll give more context into that. And specifically, what are current best practices to share research code? And I think this is something that is sometimes a bit overlooked right now. And now we have quite good best practices. So I thought that was a good opportunity to share them. But first, let's go back to our typical MR study. So we typically start by acquiring some data with our MR. Then we're going to do a number of processings, typically some phase of pre-processing where we prepare the data, maybe we motion correct it, remove artifact, put them in a standardized space and so on. We get some derived data. These are the measures we are actually interested in. And we're going to be able to ask our research question finally and get an answer. So in my case, it's in the form of brains because I work with brains, but obviously it could be any type of MR image. But now, this is our research, and we found something, and we're super excited about it, and we've built new knowledge, right? But now when we think about how we share that with the community, well, even today, with all those open science efforts, the way we share our research with the community is still mainly a scientific paper, okay? And this is what I'm going to give to the community, and basically the rest of the analysis can go away. It's not always the case. Neurodesk is an example, but in many cases, that's how it is. And of course, if you've worked with papers, and you probably have, when you start reading a paper, especially if you're really excited about it, and this is something that is close to your research, you basically end up with many, many questions. So I've put questions from my type of analysis, but which version of the software exactly was used? Oh, but the registration algorithm, which one was it? Or something that is often overlooked, the brain mask, how was this computed? We often don't describe that, but it can have a strong impact on our results. Okay, so that's one thing. But now let's say you are actually very, very interested and you want to build on these results and you try and reproduce. Sometimes it reproduces well, all is fine. But when it doesn't reproduce, then you end up with even more questions. Does it not reproduce because I didn't understand properly the methods? Or is it because I don't have access to the original data and then it's due to my data? Or is it because I'm using different computing resources? Or is this something I can't even think about? And of course, not the only one thinking about this. And of course now, well, not so nice. Knowledge building is not so bright anymore. And that's a bit sad. Of course, there have been ample efforts to support a more reproducible research, and in particular, the open science efforts. So at one end of the spectrum, when we think publications, there are a number of efforts on open access, so preprints, diamond open access, and so on. When we think about the open data, a lot of have been said around the FAIR principle, so for findable, accessible, interoperable, reusable, and this gives us best practices as to how we can package our data, we've mentioned bids as well, and make it available to others so that they are meaningful. But when we think about what's in between, that is typically represented as code, it's not so here we have a space for wondering how can we open up our code, and hopefully when we have all those pieces, we get our knowledge and excited discovery bright again. So we've chatted about reproducibility, and before I get any further, I just want to set a few definitions, because reproducibility actually means very different things to different people. So when we talk about reproducibility, basically I see that as a spectrum, and there are two ends of that spectrum. So one end is computational reproducibility. It's our ability to get the exact very same results using the same data, the same code, the same environment. You keep everything the same, and you aim at getting the same results that were obtained in the original paper or study. Replicability, on the other end, is the idea that we want to try and see if we get the same scientific findings. So here we are not, maybe the results are slightly different, but the scientific conclusions are the same, using data that is similar and a method that is similar. Of course, this is not this definition is very broad, and you have variations of that. But I think those two are very important, and probably replicability is what I would care more about in the long run, because what I want is that my scientific findings are true in different contexts and not just for my small scale study. But computational reproducibility is something that can help us on that way towards replicability. And this is what we're going to focus on right now. And of course, if you want to be able to do that, you need to share the different research artifacts that we've seen before. And so I'm going to focus on three main practices that I believe are best practices right now to share code. Of course, when we think open code, the first thing we think about is open source. Having an open source license makes the code transparent. It also provides means for others to be able to basically reuse your code. And this is the first step, and it's super important. But this is not enough to ensure that our code is open. The second step that I always try to emphasize is the idea that we need the code to be archived. So basically, when we think about research papers, when we share papers with others, we expect them to remain available in 10 years from now. If you're sharing research code, we should have set the same standard, right? You don't want your research code to be not available in 10 years from now. And if we and to be able to claim that, to make sure that it will remain available, we have to rely on archives. And there are two archives right now that I think are really easy to use, is Software Heritage and Zenodo. They are both directly connected with GitHub. And Software Heritage is trying to build this big graph of all the open source software that is available online. Again, basically putting the code only on GitHub is not enough. And why is it not enough? Because GitHub provides no guarantee that the code will remain available in 10 years from now. And it has happened in the past that versioning tools that were available to share code just stop running, and basically we end up with links that are broken links. So that was the second step. And the third one, which is a bit more broad, is the idea to try and rely on coding best practices. And this, of course, is super important if we want our code to be reusable. So I've mentioned a little bit versioning, but of course, you could archive your code without versioning it. In open science, it's always about doing step one after the other. So versioning, listing dependencies, because that's important to understand how we can rerun your code, even though it's not necessarily sufficient, and I'll get back to this. And one thing I really try to push in my projects is to try to have a README that helps newcomers being guided into how to access your code. And here, remember, we are not necessarily talking about software that are reused by others, but more about code that is attached to a paper and that you want to share so that others can better understand what was done in your paper. And in that case, I think it's really useful to have a README that is just going to describe how can I reproduce the first figure, because sometimes when you read a paper, you're just, okay, they have these results, but I'd like to change this and see if the figures still give the same type of findings. So this is a practice that sounds very simple, but when you arrive in a new repo that you don't know, having a README that is meaningful is something that's super valuable. So going back to these best practices for open code, trying to keep them as simple as possible. The first step is having open source, making the code open source, archive it for long-term preservation, and then using coding best practices. Of course, here you could go very far, but I think versioning, listing dependencies, and README are a good first step. Okay, so now that we've followed best practices, you might ask, okay, are my results computationally reproducible now? I've shared my data, I've shared my code. Well, actually, it's much more complex than that. So there is ample research that shows how differences in environments, so it could be your operating systems, could be the version of like low-level libraries, can have an impact on your final results. And this, of course, calls for the containers, which makes a nice link back with Neurodesk. And there was this challenge recently about trying to reproduce scientific papers from 10 years back. And basically, they just highlighted how difficult this could be. So sharing your source code, making it archived, using software best practice is not solving everything. But I want to say that this is also okay, because this is still a big step, because basically you're making a code transparent and it's clearer for researchers in the community to understand what you've done. And of course, we can go even further, but this can be in a second step. Okay, so we focused on two types of reproducibility. And then we can think of another aspect, which is reusability. And here I'm thinking no longer about code that is attached to a paper, but more about a software that you want to make available to the community and you want others to reuse. And here, again, we are, the bases are the same. So making a software open means, of course, first using an open source license, making the code available, and using an archive for sustainability, long-term preservation. And this answers the questions, well, who can actually access your code and use your software? But then as you're building the software, there are other questions. So one important one is who can contribute. And when we see, for instance, open source software on GitHub, people might submit pull requests, for instance, or create issues that describe their problem or features that they might want to develop. And this is called open development, and basically answer the question, who can actually contribute to the code base? You could have a software that is open source, but doesn't accept external contributions, and basically this wouldn't be open development. And then going one step further, we need to answer who can decide for future directions, and this is the question of governance of the software. So basically, when we make it very practical, when we have a pull request on GitHub, who decides whether this should be accepted or not, on the basis of what? And this is basically reflecting on who has the possibility to join the leadership of the project. Let's keep in mind that I'm not saying that people who've never used the software and are arriving one day should be straight up into leadership. What this means is that there should be pathways so that people can grow from being a user to maybe contributing and then sharing their ideas on how the software can evolve. And this is important to discuss and to consider so that we can have governance that are community-led. Oops, sorry. And this brings us to this slide that I always go back to, but basically what open science brings us. So when we chat open science, we always emphasize technical solutions, right? And of course, we do need technical solutions because that's what makes things easier. But beyond those technical solutions, open science brings a new culture, which is the fact that we start working together collaboratively. And I guess MRITogether is very much aware of that. Of course, changing culture takes time. But I think we are working in the right direction. To help us in that direction, there are a number of open science awards. I've put one here that is a French example, but I know there are examples worldwide. And I think this will help us into getting into more collaborative research. With that, this is the end of my talk. Thank you very much.